Hi, I'm Chris Williams. I'm the Software Assurance Tools Team Lead at NASA IV&V, and we're going to be talking today about the code analysis pipeline and the dependency structure matrix work that we've been doing. So we started this work because we have a lot of domain experience with static code analysis at NASA IV&V. Our team supports the different tools that our analysts and our projects run against the different NASA missions. We have experience in setting them up, configuring them, but we've always had recommendations to use more than one tool. And the NASA Engineering Safety Center and the software tech fellow, Lorraine Prokop, had come to us, and they were talking about this idea of encouraging further static code analysis within NASA at places that maybe weren't as familiar with it or didn't have as much experience. And so this idea of a code analysis pipeline, and then there's another idea that we'll talk about and demonstrate, the dependency structure matrix, that allows you to analyze source code in different contexts and from different tools to bring in the information that's relevant to you. So this is something that we really think can help. There are NASA's 7150 standards out there that address static code analysis and what projects should be doing. So this is really all about trying to make it easier for people to potentially take advantage of the available open source tools, or even COTS tools in some cases. This is a fully open source pipeline and architecture. We'll talk through and demonstrate what we've built here that would be able to be used elsewhere is the plan in the future here as we continue the work.
Hi, I'm Jerry Williams. I'm with the NASA IV&V Software Assurance Tools team. I'm the tech lead on the CAP system. I'm going to be describing the CAP architecture some and demonstrating some of the tool functionality. So this is the CAP architecture. What you're looking at are the different pieces of the CAP system. In the upper right here is the Jenkins automation server. It's responsible for running the Docker containers that execute the static analyzers and collect metrics and things like that. When that runs, it then sends the information to the central part there. You see the application server, which processes the results and puts them into a database where we combine all of the results from the different analyzers. This is all tied to the Git server, which is where we pull the code from source control. And then we also have a web browser client that is able to view the different results from the static analyzers and the metrics. And we also have a web API connected to this that allows other applications to connect to the data that is collected by the CAP. So we start an analysis in CAP from a Git repository. The one you're looking at here is just called Tech Demo. It's some source code that we have that can be publicly available. It has no security restrictions or anything like that. We have run CAP against various NASA projects, OpNav, some CFS builds, and even some projects at NASA IV&V. This source code just contains basic bugs that we can trigger the static analyzers with, some metrics collection and things like that. What we're going to do, though, once you have your code in Git, then you go into the CAP system and configure CAP to analyze that code. What I'm showing you here is the CAP web user interface. The first thing we're going to do is create a new analysis to analyze that source code in the Git repository. For this example, we're just going to call it Tech Demo. The Git connection is all the credentials and things like that that we need to communicate with Git. That's already been configured in the administration section of CAP. I'm not going to demonstrate that today. The analysis language for this is C, and then the configuration, you can put it in here right now, or you can wait and configure that later, which is what we're going to do. So once I've filled out all these fields, I can click Create Analysis, and now we have a new analysis in the CAP system for that repository of source code. I'm going to select that analysis. It brings us to the dashboard page for that analysis, Tech Demo. And there's nothing in here yet. Obviously, we have not run any static analyzers against the code. But if we go into the source view here, we can see that the source code is now available from Git. We can click on files and browse them and things like that. The next step then will be to configure CAP to run actually against this source code with the static analyzers that we choose to run. Now that your analysis has been created in CAP, the next thing we want to do is configure the tool to run the different analyzers or metrics tools. So what we're going to do then is click the analysis configuration, and this is where you would put in your configuration. It's a JSON configuration. I already have one prepared, so I'm going to paste that in and just walk quickly through this. This tells you how to build your source code. So you see build commands down here, tells it things like how to clean. And then the main thing here to take note of is it tells it which static analyzers we want to run. So we see here that NASA's ICOS is running. It allows you to tell it which checkers you want to run in that tool. We also have Facebook and FIR running with specific compile commands for running that tool. We're running CPP check, and we also run some custom analyzers. These were developed in CPP check, and they do things like collect metrics, McCabe complexity metrics, incomplete code metrics, and things of that nature. The last thing you see here is the depends tool runs. This collects information about the dependencies in the system. So once you've configured that JSON file, you'll save that configuration. And then when we're actually ready to do the analysis to finally get results, we'll go to the execution tab here. What you see here is that same configuration, so you could modify it on the fly here, decide to change the checkers you're running or the tools you're running, and you could overwrite that with any changes you make. Or another option here, and I'm going to demonstrate this, is you could also have this configuration in your source code repository if you wanted to track changes on it and things like that. So here you would check use cap folder instead of this configuration. If we look for this project, I'm going to go back to the source code view. We'll see there's a .cap folder that has a config.json. This is the same configuration that I just showed you, but it's actually in my source code repository. So if I choose to run with that, it's going to pick it up from the repo instead of from CAP's save of the configuration. The last thing you need to do is tell it your credentials. These are configured for your account in CAP, and it basically is your credentials to the source code repository so that you can access the source code securely. The last thing we want to do then, now that we're configured for an analysis, is go ahead and click the Begin Analysis button. And this is going to call out to the Jenkins automation server and send these settings over and start the analysis against the source code from the repository. We'll give that a second to go ahead and spin up. And you'll see it says a build has been started. You can check its progress here. If I click that link and open it, this is Jenkins, and the build has begun at this point.
Hi, I'm Joseph Lawson. I'm a developer working on the CAP and DSM projects. So now we've come to this screen here where we can see that the build that Jerry started is now completed. And what you're looking at is the Jenkins UI. You can see some build artifacts there I'll talk about later. Jenkins itself is an open source DevOps tool that essentially acts like a build system for us. And as far as the build system goes, when Jenkins gets a call to start a build like Jerry just started here, it actually goes to a system we use for Docker. And Docker itself is an open source tool that we use for containerization. Now, as far as the containerization goes, it's important to understand that when we build these containers, they're very specific to the environment that it's set up in. So in effect, when I set up an environment for, say, the system that requires a very particular library, I can set that up and I don't have to worry about conflicts with any other system. So when we set up this particular tech demo, we had a very specific build system that we used for it. And that system will then take in the source code. It will run a series of analyzers like CPP check. It'll run infer and ICOS. It'll get those results out and it will send it back to Jenkins. So once Jenkins gets those results back in the build artifacts, you can see here that there is a checkers.serif, cppcheck.serif. These are all just results that the analyzers have sent from the Docker container back into Jenkins, and now it's available for storage. From the storage, you can download these as you wish. There isn't too much a constraint on how these are used. If you prefer to download them, or you can send them to the cap results system where you can view them inside of the cap results work, you can do that as well. So there's a variety of different ways you can handle this. It's even as far as the builds go, we can set this up in a variety of different ways. So you can set it up manually, like Jerry did, where you can hit a button and it'll start an analysis, where you can start these up nightly. You can start these when a commit gets pushed. You can start these in a very specific hour of the day. It all works on a cron job framework if you understand what that means. So you have a variety of different ways you can understand this stuff. So when Jenkins finally finishes the build, the results are then sent over to cap results, which Jerry will talk about more.
Okay, so we've completed our analysis and we've taken these results from the Jenkins build and we've sent them to the CAP system. I'm going to switch over to the CAP user interface now, and you see that we now have 123 potential issues identified by that analysis. So what you see down here are the different graphs detailing those issues by things like current status, severity, and the specific tools that were used to find the individual errors.
And Jerry, on those tools that we have there, those are all open source. CPP check is open source. That we did some custom checks and things you'll talk about here in a minute too, that we're using Python add-ons, they call them. Infer is one Facebook uses against its huge code base. ICOS is those two though. CPP check, Infer are a little bit more like bug finder type tools. ICOS is one that Ames developed, NASA Ames. It's more of a sound analyzer, similar to MathWorks Polyspace, if you've ever used that one, where you can identify potentially the absence of a runtime defect in a critical piece of code. It works a little differently. It's more complex, but we're able to use all of those, and even COTS tools. We've integrated those for our own IV&V program use, Clockwork, Code Sonar, so we can use any type of tool here within the pipeline.
Okay, thanks, Chris. What I'm going to do here is just drill down through severity. This might be one approach you take to sort of prioritize looking at these static analysis results. So I'm going to click the error segment, and this is now showing me just the ones that were identified as errors. So just looking through this user interface here, this is where we look at the source code and we look at those analysis results in context of the source code. So if I click the first one that reported here, we'll see here's the source code, and right below it is the finding. This one actually came from the ICOS tool. You see there's a CWE, a common weakness enumeration tag to it. I could click on that and go to their website and read about what that means. This one selected right now has already been statused to create an IV&V issue. You might look at that and determine it's a false positive or it needs a review or something like that. This is where you would do that in the upper left here. Set your status, maybe make a comment on it, and you can see there's also some comments here. People on the team can collaborate with one another on individual findings to determine how they might mitigate that on their project. Another part of the system here over on the left side is the directory structure that came from the Git repository. So we can browse through that and select individual files that we're interested in. I'm going to show you an example here, divide by 0 tests that we did. If you scroll through this, you'll see that there's findings from each of the analyzers. There's an interesting result down here. You'll see there's results here from Infer, CPP check, and ICOS all in this piece of code here. One interesting thing here is you see on the same line, the same type of error is reported by Infer and CPP check. This goes back to what we always say, is that it's best to run multiple static analyzers if you can against your source code, because they have different strengths between them, like Chris mentioned. But also, if you have multiple analyzers reporting a similar result on the same line, it can give you some confidence that that is an actual true positive result that you need to focus on. The other example I'll show here quickly in this metrics file is where we do different metrics collections using CPP check add-ons. You can see this function here has been tagged as a high complexity function. It has a McCabe complexity value of 11, which is greater than a threshold level that we set for the code. So that's another bit of data that we're collecting for the system and displaying to you in this user interface. I'm going to describe the dependency structure matrix or DSM capability we've added to the system. What a DSM basically does is it's a visualization for dependencies in your system, the same as a software dependency graph does with nodes and edges. But as you can see, if your system grew very large, you're going to have a big unwieldy graph that you have to deal with. The point of a DSM is to put that in a tabular matrix form to make the dependencies a little more easy to see. So for example, here we see that component A depends on component B, D, F, G, and L. What we're going to look at now is in the system where we've implemented this capability. Okay, so what we're looking at now is the Dsm view in the system, and this is based on source code files in the system. And what we're able to do in here is a few different things. We can change the dependency types that the relationships are based on. So right now this is based on calls and implementation links. You could do imports, returns, casts, things like that. We're going to go with the default. You can also resequence the DSM by changing the algorithm that's used. So I'm going to change that. And what this one does here is it tries to partition the DSM so that all of the dependency information falls below the diagonal. And essentially what that means is that anything that is below the diagonal doesn't have relationships to each other. If something is above, then we see there's a cyclic relationship between the two. So if I hover over this, we see that log.c depends on mathfunctions.c, and just below the diagonal, we see mathfunctions.c depends on log.c. So what you can do in CAP is click on those to navigate to the code. So if I click mathfunctions.c, we'll go to the source code. We see that mathfunctions.c has a function called double positive that calls the log function. If we go back to the DSM then and look at log.c, we see it has a function that calls the same double positive function from mathfunctions.c. So we know that there's a cyclic dependency there, which is generally not a good thing. So this is an area where you might want to refactor your source code. The problem with this is when you get a lot of files in a large project, your DSM matrix is going to become very big. So what we wanted to do to fix that is map these source code files to logical components. So instead of looking at the source code level, we can start looking at things like an architectural level, where different files in the system are mapped to architectural components. So we've added a capability to CAP that lets us map source code files to logical components like architecture. What you're seeing here is an example DSM based on components instead of just source code files. This is a core flight executive app. The source code for it was used to generate this DSM. And what you see here is we still have the relationship data between files, but now they also apply to components. So if I mouse over a component, you'll see the green highlighting there to show just the files that are mapped to that component. So like common here is a component, and we'll see that the different files like file 11 CFS app has 414 dependencies on files that are part of the common logical component. That makes sense because it contains things like app utils and different utility functions. So you see app utils has a lot of the bulk of the relationships are to there. So one of the things that we can get with this then, even if in a large system like this, because it's components now instead of just files, you get a much more compact DSM, and you can look at the relationships between components now instead of just files. We looked before and we saw that we have things like McCabe's cyclomatic complexity. So some of the things that we intend to do are identify maybe hotspots in the code. For example, maybe you have two components that are related to each other, that both have high cyclomatic complexity, we would put an indicator on those files and their components and say, hey, this is a spot in your system you may want to apply some analysis focus to see if you might have a potential problem here. So this is ongoing work and things we're going to be working on this year to make the DSM capability much more production ready. The last part of the system we wanted to demonstrate today, this is ongoing work, things we expect to be doing during this year, is this idea of a management level report. So at this point, the whole basis of the CAP, what you're trying to do is improve the quality of your source code. So you're gathering static analysis findings, you're collecting metrics, all with the aim of making your code higher quality. Because we've collected all of that data in a central database from all the analyzers, we've collected metrics against the source code, and we've collected dependency information, we can now take that information and generate a report directly from it. So this is an example of a report we've been working on, the Code Quality and Risk Report, that does take that data and tries to present it in a way that lets you see the current state of your system and metrics about the quality of your source code at this point in time. So what we're going to do is just sort of go down through this report and give you an idea of the types of things that we expect to be able to report based on the data that we're capturing in CAP currently and data that we intend to start capturing as we continue development this year. So what you see in this report, the static analysis summary is a basic summary of the current state of your analysis. So you're going to see things like the breakdown of the issues that were identified against your source code, how many of those have been reviewed by your team and what the current status is, breakdowns by finding type or severity, and then even specific files that maybe have an excessive number of potential problems that were identified by the analysis, or even ones where your team said, yes, this is actually a problem. And also following that logical component structure that we talked about, we can point out specific architectural components in the system and let you know that there's a significant number of static analysis findings against individual components. Then we're going to summarize your source code metrics. So things like cyclomatic complexity that we looked at, we'll be able to tell you, a number of functions in your source code that exceed a certain complexity threshold. We'll be able to point out specific files that have functions that pass that threshold. And again, logical models in your architecture that may be the files that are mapped to that logical component exceed a specific threshold. And then even down to the level of which functions have those high complexities. Other data we can collect is like slot counts for your source files. And then there's another number of metrics that we plan to collect as well that's not represented in this prototype report at this time. We also want to take the dependency information that we looked at that we used to populate the DSM. We can also take that same data and tell you about maybe cyclic dependencies that are in your source code as part of this report. We can do the hotspot analysis that we talked about. And again, that's places in your source code where maybe there's dependencies between components or files in the system, and those components have certain concern areas like high cyclomatic complexity, or maybe there's a high number of potential defects from the static analyzers. Those would be places a manager might look at this report and say, hey, there's some areas here in the system that we want to apply some focus to. Other areas that are metrics related, maybe cohesion and coupling. We want high cohesion and low coupling. We can use that dependency information to look for those types of areas. And the last section of this report is code quality and risk over time. This is where we intend to take all that data that we've gathered in the database, the historical data, and show you how these metrics and findings have changed over time as your progress changes on your project. Okay,
thanks, Jerry. Thanks everyone for watching this today. My This is Chris Williams, the Software Assurance Tools Team Lead again, and my contact information will be there. If you have any questions or comments for our team, feel free to reach out. Thank you.